You think you're sitting in a chair right now. You think your feet are touching the ground. You think you're holding your phone or resting your hands on a desk. But here's the truth. None of that is actually happening. Not in the way you think. You have never touched anything in your entire life. Not once. Not ever. Your hand has never made contact with another person's hand. Your feet have never made contact with the floor. The atoms in your body have never made contact with the atoms in anything else. There's always a gap. Always. A tiny, impossibly small gap. But a gap nonetheless. And this isn't philosophy. This isn't a metaphor. This is physics. Hard, experimental, verified physics. Richard Feynman, one of the greatest physicists who ever lived, explained this. And once you understand it, you can't unsee it. It changes how you perceive everything. Every handshake, every hug, every step you take. None of it is what it seems. So, let's talk about what's really happening when you think you're touching something. Because the answer is far stranger than you imagine. Here's the setup. You're holding a cup of coffee. You feel the warmth of the ceramic against your skin. You feel the weight of the cup. You feel the texture of the surface. Your brain tells you, I am touching this cup. And in everyday language, that's fine. That's accurate enough. But zoom in. Go down to the atomic level. Look at what's actually happening between the atoms in your hand and the atoms in the cup. And you'll see something shocking. They're not touching. They never get close enough to touch. There's a force, an invisible force, pushing them apart, keeping them separated by a gap so small you could never see it, but a gap that is always there. Always. This force is called the electromagnetic force, and it's one of the fundamental forces of nature. It's the same force that makes magnets stick to your fridge, the same force that makes lightning arc through the sky, the same force that holds atoms together, and it's the force that prevents you from ever truly touching anything. Here's how it works. Every atom is made of a nucleus, protons and neutrons at the center, and orbiting that nucleus are electrons, tiny, negatively charged particles. Now, when two atoms get close to each other, their electron clouds start to interact. And here's the key. Electrons are negatively charged, and like charges repel. You've seen this with magnets. If you try to push two north poles together, they push back, they resist, they don't want to get close. Electrons do the same thing. When the electron cloud of one atom gets near the electron cloud of another atom, they repel each other strongly. And this repulsion is what you feel as solidity. This is what you experience as touch. The sensation of touch is not atoms making contact. It's atoms pushing each other away. The electromagnetic repulsion between electron clouds creates a force, and that force pushes back on your hand. Your nerves detect that force, and your brain interprets it as the feeling of touching something, but the atoms never actually touch. They're separated by a gap maintained by electromagnetic repulsion. Let me give you a sense of scale. The nucleus of an atom is incredibly small. If you scaled an atom up so that the nucleus was the size of a marble, the electron cloud would extend out about half a mile in every direction. The atom is almost entirely empty space, and the electrons are zipping around in that space, but they're so small and so far apart that even they are mostly just empty space. So when you press your hand against the table, you're not pushing solid matter against solid matter. You're pushing clouds of electrons against clouds of electrons. And those clouds are mostly empty space. It's emptiness pushing against emptiness. And the force you feel is just the electromagnetic repulsion between the outer electrons of the atoms in your hand and the outer electrons of the atoms in the table. That's it. That's what touch is. A force, not contact. Now here's where it gets even stranger. The atoms in your hand and the atoms in the table never even get close to the point where their electron clouds overlap significantly. The repulsion kicks in long before that. The force increases as the atoms get closer. The closer they get, the stronger the repulsion. And the force increases so steeply that the atoms can't get past a certain distance. They hit a wall, an invisible electromagnetic wall. This is why solid objects feel solid. It's not because they're made of continuous, impenetrable matter. It's because the electromagnetic repulsion between atoms creates an effective barrier. A barrier that feels completely solid to you, but is actually just a force field. Feynman explained this beautifully. He said, when you sit in a chair, you're not really sitting on the chair. You're floating above it, hovering, suspended by electromagnetic forces. The atoms in your body and the atoms in the chair are repelling each other, and that repulsion holds you up. You're levitating, just a tiny, tiny distance above the chair, so small that you could never measure it with any normal tool, but it's there. You are not in contact with the chair, you're being held up by an electromagnetic force field, and this applies to everything. When you stand on the ground, you're not touching the ground, you're hovering above it. When you hold a pen, you're not touching the pen, you're levitating it with the electromagnetic repulsion from your hand. Every single interaction you have with the physical world is mediated by forces, not by contact, by invisible fields of force that push things apart. Now you might be thinking, okay, fine, atoms don't touch, but that's just a technicality. I still feel like I'm touching things. And yes, that's true. Your experience of touch is real. The sensation is real, but the mechanism is not what you think it is. And understanding the mechanism changes everything. Because once you realize that touch is just electromagnetic repulsion, you start to see the world differently. You realize that the solidity of matter is an illusion. A very convincing illusion, but an illusion nonetheless. Solid objects are mostly empty space, and the forces that make them feel solid are the same forces that govern electricity, and magnetism, and light. It's all connected. It's all the same fundamental physics. Here's another way to think about it. Imagine you have two incredibly powerful magnets, and you try to push the north poles together. You can feel the force pushing back, you can feel the resistance, but the magnets never touch. There's always a gap, a layer of air between them, and the force gets stronger the closer you push them. That's exactly what's happening at the atomic level when you touch something. The electromagnetic repulsion between atoms acts like magnets pushing against each other. You feel the force. You interpret it as solidity, but there's no actual contact, just force. Now let me address something you might be wondering. If atoms don't touch, how do things stick together? How do molecules form? How does chemistry work? Good question. The answer is that while atoms don't touch, in the sense of their electron clouds merging, they do interact. Electromagnetic forces can be attractive as well as repulsive. When atoms get close enough, the electrons can rearrange themselves in ways that create attraction. This is called bonding. Chemical bonds are electromagnetic forces that hold atoms together in molecules. But even in a chemical bond, the atoms are not touching. They're held at a specific distance by a balance of attractive and repulsive forces. The electrons are shared or transferred, but the atoms themselves remain separated. There's still a gap, always. Here's what happens. In a covalent bond, two atoms share electrons. The electrons spend time in the space between the two nuclei, and this creates an attractive force that pulls the atoms together. But there's also repulsion. The nuclei repel each other because they're both positively charged, and the electron clouds repel each other. So the atoms settle at a specific distance where the attraction from the shared electrons exactly balances the repulsion from the nuclei and the rest of the electron clouds. That distance is the bond length. And it's not zero. The atoms are separated. They're held together by forces, but they're not touching. The same thing happens in ionic bonds, in metallic bonds, in every type of chemical interaction. Atoms are held together by electromagnetic forces, but they never actually touch. The forces create the structure. The forces give matter its properties, but contact? No, never. Now let's go deeper, because there's another level to this that's even more mind-bending. Even if you try to force atoms together, even if you applied unimaginable pressure, even if you squeezed and compressed and pushed with all the force in the universe, the atoms still wouldn't touch. Here's why. As you push atoms closer together, the electromagnetic repulsion increases dramatically. The force grows stronger and stronger, and it grows so fast that it becomes nearly impossible to compress matter beyond a certain point. You'd have to overcome the electromagnetic force, and that force is enormous. To give you a sense of scale, the electromagnetic force is one of the strongest forces in nature. It's about 10 to the power of 36 times stronger than gravity. Gravity is the force that holds planets in orbit, that keeps galaxies together. And the electromagnetic force is trillions of times stronger. So, when you try to push atoms together, you're fighting against one of the most powerful forces in the universe, and you lose. But wait, there are situations where atoms do get compressed, in the cores of stars, for example, in white dwarfs and neutron stars. What's happening there? Good question. In those extreme environments, gravity is so strong that it can overcome the electromagnetic repulsion between atoms. The atoms get crushed together, the electron clouds collapse. And in a white dwarf, the electrons are pushed into a state called electron degeneracy. They're packed as tightly as the laws of quantum mechanics allow. But even then, the electrons don't touch each other. They're in a degenerate state where quantum pressure holds them apart. It's a different kind of force, a quantum force, but it's still a force, still a repulsion, still keeping the electrons separated. In a neutron star, the pressure is even greater. The gravity is so intense that it overcomes even electron degeneracy. The electrons are forced to merge with protons, forming neutrons, and the star becomes a ball of neutrons packed together. But even here, even in this extreme state, the neutrons don't touch. They're held apart by neutron degeneracy pressure. Another quantum force? The universe seems to have layers of forces, each one preventing contact at different scales. And no matter how hard you push, no matter how extreme the conditions, there's always a force pushing back, always a gap. The only exception, the only place where matter truly collapses without limit, is inside a black hole. Inside the event horizon of a black hole, gravity is so strong that it overcomes every force. Electromagnetic repulsion, electron degeneracy, neutron degeneracy, everything. The matter collapses down to a point, a singularity, infinite density, zero volume. And at that point, our physics breaks down. We don't know what happens. We don't have a theory that describes it. But that's the only scenario where the gaps disappear, where the forces can't push back anymore. Everywhere else in the universe, there's always a gap, always a force maintaining separation. Let's talk about what this means for your everyday experience. When you walk across the floor, you're not actually touching the floor. The atoms in your shoes are being repelled by the atoms in the floor, and that repulsion creates an upward force, a normal force. This force pushes up on your foot with exactly the same strength as the force of gravity pulling you down, and the two forces balance. You don't fall through the floor, but you also don't touch the floor. You're suspended, hovering, floating on an electromagnetic cushion. When you pick up a glass of water, you're not touching the glass. The electromagnetic repulsion between the atoms in your hand and the atoms in the glass creates a force, and that force supports the weight of the glass. Your hand pushes on the glass with electromagnetic force. The glass pushes back with electromagnetic force, and the glass stays in your hand. But there's no contact, just forces. Invisible fields of force interacting. When you hug someone, you're not touching them. The atoms in your body and the atoms in their body are repelling each other, and that repulsion creates the sensation of warmth, of pressure, of closeness. But the atoms never touch. There's always a gap. You're two clouds of atoms, mostly empty space, pushing against each other with electromagnetic forces. And your brain interprets that as a hug. This is the reality of touch. It's not contact, it's force, electromagnetic force, and once you understand this, you can't unsee it. Every interaction you have with the physical world is mediated by these invisible forces. You're surrounded by force fields. You're made of force fields. And everything you touch is just force fields interacting with force fields. Matter pushing against matter without ever making contact. Now here's the part that really drives this home. Light, visible light, the light you see with your eyes. It's also electromagnetic. Light is electromagnetic radiation. It's waves of electric and magnetic fields oscillating through space. And the same force that prevents your hand from touching a table is the force that creates light. The electromagnetic force governs both. When you see something, photons of light are bouncing off it and hitting your eyes. And those photons are created by electrons in atoms moving between energy levels. Electromagnetic interactions. When you touch something, electrons in your hand are repelling electrons in the object. Electromagnetic interactions. It's the same force, the same physics. Seeing and touching are both mediated by the electromagnetic force, just in different ways. Feynman loved pointing this out. He'd say, you think seeing and touching are completely different senses, but they're not. They're both electromagnetic interactions. Your eyes detect electromagnetic waves. Your skin detects electromagnetic forces. It's all the same fundamental phenomenon. The universe is simpler than it appears. There aren't dozens of different kinds of forces and interactions. There are just a few fundamental forces. And the electromagnetic force is one of the most important. It governs chemistry. It governs light. It governs touch. It governs the structure of matter. Almost everything you experience in daily life is electromagnetic. Here's something else. The electromagnetic force is why matter has the properties it does. Why some things are hard and some things are soft. Why some things conduct electricity and some things don't. Why some things are transparent and some things are opaque. All of these properties come from how electrons in atoms interact with electromagnetic fields. A diamond is hard because the carbon atoms are bonded together in a very strong, rigid lattice. The electromagnetic bonds are strong. It takes a lot of force to break them. A pillow is soft because the molecules are loosely connected. The electromagnetic forces holding them together are weak. It's easy to compress. Metals conduct electricity because some of their electrons are free to move. They're not bound tightly to individual atoms. They can flow through the material, carrying electric current. That's an electromagnetic phenomenon. Glass is transparent because photons of visible light can pass through it without being absorbed. The electrons in glass don't interact strongly with visible light. So the light goes right through. That's electromagnetic. Every property of matter, every characteristic, every behavior, it all comes back to the electromagnetic force. And that force is what prevents atoms from touching. It's what creates the illusion of solidity. It's what makes the world feel the way it does. Now, let's address the obvious question. If nothing ever touches, what does it even mean to say something is solid? What is solidity? Good question. Solidity is not about atoms being in contact. Solidity is about resistance to deformation. A solid object resists being compressed. It resists being bent or stretched or broken. And that resistance comes from the electromagnetic forces between atoms. When you press on a solid object, you're pushing the atoms closer together. And the electromagnetic repulsion increases. The atoms push back. And if you push hard enough, you either compress the object slightly or you break it. But in both cases, it's the electromagnetic forces doing the work. Solidity is a macroscopic property that emerges from electromagnetic interactions at the atomic level. It's not about contact, it's about force. A liquid is different. In a liquid, the atoms or molecules are free to slide past each other. The electromagnetic forces are still there, but they're not arranged in a rigid structure. So when you press on a liquid, the molecules move out of the way. The liquid flows. It doesn't resist compression the way a solid does. But even in a liquid, the atoms don't touch. They're still separated by electromagnetic repulsion. They're just free to rearrange. A gas is even more extreme. In a gas, the atoms or molecules are far apart. They're flying around at high speed, bouncing off each other. But when they bounce, they're not making contact. They're repelling each other electromagnetically. Each collision is an electromagnetic interaction. The atoms get close, the repulsion kicks in, and they bounce apart. No contact, just force. And this is true for every phase of matter: solid, liquid, gas, plasma. In every case, the atoms are separated by electromagnetic forces. Contact never happens. Here's where it gets philosophical. If nothing ever touches, if all interactions are mediated by forces, what does that say about the nature of reality? What does it mean for something to be real? Is the world just forces and fields? Are particles even real, or are they just localized disturbances in fields? Feynman would say, don't get too hung up on this. The math works. The predictions match experiments. That's what matters. Whether you call it particles, or fields, or forces, the physics is the same. The universe behaves the way it behaves. Our job is to describe it accurately, not to satisfy our intuition about what's real. And the accurate description is this: matter is mostly empty space. Atoms are mostly empty space. The forces that make matter feel solid are electromagnetic. And those forces prevent atoms from ever touching. That's the reality, whether it matches your intuition or not. But here's the beautiful part. This isn't abstract philosophy. This is testable. This is measurable. We can observe the electromagnetic force in action. We can measure the repulsion between atoms. We can calculate the distances. We can predict how matter will behave under different conditions. And the predictions work every time. The theory of electromagnetism, developed by people like Faraday and Maxwell and Feynman, is one of the most successful theories in all of physics. It explains everything from how magnets work to how light propagates to why you can't walk through walls. And it all comes back to one fundamental fact. Charged particles create electric fields, moving charges create magnetic fields, and these fields exert forces on other charges. That's it. That's the foundation. Everything else is just consequences of that basic principle. And one of those consequences is that atoms with negatively charged electron clouds repel each other. They can't touch. They're kept apart by the electromagnetic force. Let me give you another example to make this concrete. You've probably heard of the Pauli exclusion principle. It's a quantum mechanical rule that says no two electrons can be in the same quantum state at the same time. This principle is responsible for a lot of the structure of matter. It's why atoms have different energy levels. It's why electrons fill up orbitals in a specific way. And it's part of why matter resists being compressed. When you try to push atoms together, you're trying to force electrons into the same space. But the Pauli exclusion principle says they can't be in the same state. So they resist. This resistance is quantum mechanical, not purely electromagnetic, but it works together with the electromagnetic repulsion. Both forces push back when you try to compress matter. Both forces prevent atoms from touching. The universe has multiple layers of defense against contact. Classical electromagnetic repulsion, quantum degeneracy pressure, and at the most extreme scales, other quantum effects. The universe really doesn't want atoms to touch. Now let's talk about what Feynman would say about all this. Feynman was famous for his ability to explain complex physics in simple terms. He'd give these lectures where he'd take the deepest, most abstract ideas and make them accessible. And he had a particular gift for pointing out where our intuition is wrong. He'd say, "You think you understand something because you have a picture of it in your mind. But that picture is probably wrong. Nature doesn't care about your picture. Nature does what nature does. And your job is to update your picture to match reality, not to force reality to match your picture. And when it comes to touch, our intuitive picture is completely wrong. We imagine atoms as little hard balls bouncing off each other, making contact. But that's not what's happening. Atoms are clouds of probability. Electrons are not little balls orbiting a nucleus. They're wave functions, probability distributions. And when two atoms get close, their wave functions interact. The interaction is electromagnetic, and the result is repulsion, a force, but no contact. The intuitive picture fails. The correct picture is stranger. And Feynman would say, get used to it. Physics is strange. Reality is strange. And the more you learn, the stranger it gets. Here's another example Feynman loved. Magnets. When you hold two magnets close together, you can feel them pushing or pulling. And you ask, how do they do that? How does one magnet affect the other across empty space? And the answer is fields, magnetic fields. The magnet creates a field in the space around it, and that field exerts a force on the other magnet. It's action at a distance, but mediated by a field. And Feynman would say, this is exactly what's happening when you touch something. Your hand creates an electromagnetic field. The object creates an electromagnetic field. The fields interact, and the interaction creates a force. You feel the force, and you call it touch. But it's the same physics as magnets pushing each other, just on a much smaller scale. And once you see that connection, once you realize that touch is just electromagnetic force, the mystery disappears. It's not mysterious, it's just fields and forces. The same fields and forces that govern magnets and light and electricity. It's all connected. It's all the same fundamental physics. Now, I want to address a common objection. Someone might say, okay, atoms don't touch in a literal sense, but surely molecules touch. Surely when I grab a doorknob, the molecules in my hand are in contact with the molecules in the doorknob. But no, that's not right either. Molecules are made of atoms, and atoms are held together by electromagnetic forces. So molecules are just clusters of atoms held together by forces. And when two molecules interact, it's the same story. Electron clouds repel. Electromagnetic forces create the sensation of contact. But the molecules don't touch any more than the atoms do. It's forces all the way down. No matter what scale you look at, whether it's atoms or molecules or macroscopic objects, the story is the same. Electromagnetic forces create the illusion of solidity. But there's no actual contact, just fields interacting with fields. Here's a thought experiment. Imagine you had perfect, infinitely precise control over the position of atoms, and you tried to push two atoms together until they touched. What would happen? As you push them closer, the electromagnetic repulsion would increase. The force would get stronger and stronger, and you'd have to apply more and more force to push them closer. At some point, the repulsion would be so strong that you couldn't push them any closer without doing something extreme. You'd have to input enormous energy, and if you kept pushing, eventually you'd have to overcome the electromagnetic force entirely. And to do that, you'd need energies comparable to what happens in particle accelerators or in the cores of stars. And even then, you wouldn't get the atoms to touch. You'd break them apart. You'd ionize them, stripping off electrons. Or you'd smash them together so hard that they'd undergo a nuclear reaction. But the atoms themselves would never touch. The forces would either push them apart or destroy them before they could make contact. There's no scenario where atoms just touch. It's not physically possible. The universe is structured in such a way that contact is forbidden. Forces mediate all interactions, always. Let's think about this from another angle: energy. When you push two atoms together, you're doing work against the electromagnetic force. You're inputting energy, and that energy gets stored as potential energy. The closer the atoms get, the more potential energy they have. And if you let go, the atoms spring apart. The potential energy converts back to kinetic energy. The atoms move away from each other. This is exactly like compressing a spring. You push the spring together, it resists, you do work, the energy gets stored, and when you let go, the spring expands. Atoms work the same way. The electromagnetic force acts like a spring. It resists compression. It stores energy. And it pushes the atoms apart when you release the force. This is why matter is elastic. Why objects return to their original shape after being deformed. The electromagnetic forces between atoms act like springs, always trying to restore the equilibrium configuration. And this is all because of the electromagnetic force. The force that prevents contact. The force that mediates all interactions at the atomic level. Now here's something most people don't realize. The sensation of touch is actually mediated by nerve cells in your skin. These nerve cells have mechanoreceptors, tiny structures that respond to mechanical deformation. When you press your hand against a table, the electromagnetic repulsion between the atoms in your hand and the atoms in the table creates a force, and that force deforms the skin on your hand, just slightly. The mechanoreceptors detect that deformation. They send electrical signals to your brain, and your brain interprets those signals as the sensation of touch. But what's actually happening is that electromagnetic forces are deforming your skin, and nerve cells are detecting the deformation. The whole process is electromagnetic. The force between atoms is electromagnetic. The nerve signals are electrical, which is also electromagnetic. Your brain processes the signals using electrical activity, also electromagnetic. Touch, from the atomic level to the neural level, is entirely electromagnetic. There's no contact anywhere in the process, just forces and fields and electrical signals. And yet, your brain constructs the experience of touch. The sensation feels immediate. It feels direct. It feels like you're making contact with the world, but you're not. You're detecting electromagnetic forces, and your brain is interpreting those forces as touch. It's an illusion, a very convincing illusion, but an illusion nonetheless. Feynman would point out that this is one of the great triumphs of physics. We can explain subjective experience in terms of objective physical processes. We can trace the sensation of touch from the electromagnetic repulsion between atoms, through the deformation of skin, to the activation of mechanoreceptors, to the electrical signals in nerves, to the processing in the brain. Every step is understood. Every step is described by known physics. There's no mystery, no magic, just fields and forces and biological structures responding to those forces. And the fact that we can explain it, the fact that we can describe the entire chain of causation is remarkable. It shows the power of physics, the power of science. We can take something as subjective and personal as the sensation of touch, and we can reduce it to electromagnetic interactions between particles. That's astonishing. But here's the thing. Knowing the physics doesn't diminish the experience. You can understand that touch is electromagnetic repulsion and still enjoy a hug. You can know that your hand is hovering above the table and still feel the solidity of the wood. The subjective experience remains. The physics just explains the mechanism. It doesn't replace the experience, it enriches it. Because now you know what's really happening. You know that the universe is far more intricate and subtle than it appears. You know that every touch is a dance of electromagnetic forces. Every sensation is the result of fields interacting. Every moment of physical contact is a reminder that the universe is made of forces, not solid matter. And that's beautiful. That's profound. It changes how you see the world, not in a way that makes it less real, but in a way that makes it more amazing. Let me give you one more example to drive this home. When you shake someone's hand, what's happening? The atoms in your hand and the atoms in their hand are getting close. The electron clouds start to overlap. The electromagnetic repulsion kicks in. The force increases. Your hand pushes against their hand. Their hand pushes back. The force is transmitted through the bones and muscles in your arm. Your brain detects the force and interprets it as a handshake. But the atoms never touch. There's always a gap. Always a force pushing the atoms apart. And yet, the handshake feels real. It is real. The force is real. The sensation is real. But the contact? No. The contact is an illusion. A very convincing, very useful illusion. But an illusion nonetheless. Now, you might be wondering, does this apply to everything? What about subatomic particles? What about quarks and electrons themselves? Do they touch? And the answer is, we don't know. At the smallest scales, our understanding of physics changes. We enter the realm of quantum mechanics and quantum field theory. And in that realm, the concept of touch becomes even more ambiguous. Particles are not little billiard balls. They're excitations in quantum fields. They don't have sharp boundaries. They don't have definite positions. They're described by wave functions, probability distributions. And when particles interact, it's not through contact. It's through the exchange of other particles, force carriers, photons, gluons, W and Z bosons. Particles interact by exchanging these force carriers, and the exchange creates forces. Electromagnetic force is mediated by photons. The strong nuclear force is mediated by gluons. The weak nuclear force is mediated by W and Z bosons. But even in these interactions, there's no contact. Just exchanges of particles. Just forces. The universe at every scale is built on forces and fields, not on contact. So here's the summary. You have never touched anything. Atoms don't touch. Molecules don't touch. Objects don't touch. Every interaction is mediated by forces. Electromagnetic forces at the scale of atoms and molecules. Quantum forces at the scale of subatomic particles. But never contact. The sensation of touch is real. The force is real. But the contact is an illusion. Your brain constructs the experience of touch from electromagnetic forces. And that construction is so convincing that you believe you're touching things, but you're not. You're detecting forces. You're hovering above everything you think you're touching, suspended by invisible fields of electromagnetic force. And once you understand this, you can't unsee it. Every time you pick up an object, you'll remember. The atoms aren't touching, it's just forces. Every time you walk across the floor, you'll remember. You're levitating. Just a tiny, imperceptible distance, but levitating nonetheless. And that's the reality. That's the physics. That's the universe we live in. Now, why does this matter? Why should you care that atoms don't touch? Because it reveals something fundamental about the nature of reality. The world is not made of solid stuff. It's made of fields and forces. Matter is mostly empty space. The solidity you experience is an emergent property of electromagnetic interactions. It's not intrinsic to the atoms. It's a consequence of the forces. And understanding this changes how you think about everything. It changes how you think about matter, about energy, about the relationship between things. You realize that the universe is far more subtle and interconnected than it appears. That everything is influencing everything else through invisible fields. That the void between objects is not empty. It's full of fields, electric fields, magnetic fields, gravitational fields, quantum fields. The universe is a tapestry of fields, all interacting, all influencing each other. And we are part of that tapestry. We are excitations in those fields. We are patterns of energy and force. And every interaction we have is mediated by those same fields and forces. Feynman understood this deeply. He spent his entire career exploring the nature of forces and fields. He developed quantum electrodynamics, the theory that describes how light and matter interact. He showed that you could calculate the probability of any electromagnetic interaction by summing over all possible paths a particle could take, all possible ways the interaction could happen, and the math works perfectly. It predicts experimental results to extraordinary precision. It's one of the most accurate theories in all of science, and it all comes from understanding that particles interact through the exchange of photons, that forces are mediated by fields, that contact is an illusion. The universe is built on forces, not on solid matter colliding with solid matter. And once you accept that, once you internalize it, the universe makes more sense. The strangeness becomes clarity. Here's the final piece. This understanding, this recognition that touch is force and not contact. It's not just an academic curiosity. It has practical implications. It explains why materials have the properties they do, why some things are hard and some are soft, why some things conduct electricity and some don't. It explains chemistry, how atoms bond, how molecules form, how reactions happen. It explains friction, why surfaces resist sliding against each other. Friction is electromagnetic forces between atoms on the two surfaces. It explains adhesion, why glue sticks, why tape holds things together. Adhesion is electromagnetic attraction between molecules. Every property of matter, every phenomenon you encounter in daily life comes back to electromagnetic forces, and those forces are what prevent atoms from touching. So, understanding that atoms don't touch is not just a philosophical point. It's the key to understanding how the world works. It's the foundation of chemistry, of material science, of much of engineering and technology. And it all traces back to one simple fact. Electrons repel each other. Charged particles create forces. And those forces mediate all interactions at the atomic level. So the next time you pick up your phone, remember, you're not touching it. You're levitating it with electromagnetic forces. The next time you sit in a chair, remember, you're floating above it, suspended by the repulsion between atoms. The next time you shake someone's hand, remember, the atoms in your hand and the atoms in their hand never make contact. They push against each other with invisible forces, and your brain constructs the sensation of touch from those forces. This is the reality. This is the universe. And it's far stranger and more beautiful than we ever imagined. Feynman knew this. He spent his life trying to explain it, to help people see the universe as it really is, not as it appears to our intuition, but as it is revealed by careful observation and rigorous mathematics. And the universe he revealed is a place where nothing ever touches, where forces and fields are fundamental, where matter is mostly empty space, and where the solidity of the world is an emergent property of electromagnetic interactions. That's the truth. And once you know it, you can never forget it. You'll never experience touch the same way again. And that's okay, because the new understanding, the deeper understanding, is more amazing than the illusion. The universe is not less magical when you understand the physics. It's more magical, because the physics reveals layers of complexity and beauty that you could never have imagined. And that's what Feynman wanted us to see. The beauty of the universe, the elegance of the laws that govern it, the astonishing fact that we, creatures made of atoms, can understand the forces that govern atoms, that we can decode the language of nature, that we can discover truths that are not obvious, that are not intuitive, but that are fundamental to how reality works. And the truth about touch is one of those fundamental truths, You have never touched anything. You never will, and now you know why. But let's go even deeper, because there's more to this story. There's a quantum mechanical aspect that makes the whole thing even stranger. Remember when I said atoms are mostly empty space? That's true, but it's actually more subtle than that. Because at the quantum level, particles don't have definite positions. An electron in an atom doesn't orbit the nucleus like a planet orbits the sun. That's the old picture, the Bohr model. It's wrong. The correct picture is that the electron exists in a probability cloud. It has a certain probability of being found in different locations. And that probability is described by a mathematical function called a wave function. The wave function tells you where the electron is likely to be, but it doesn't tell you where it definitely is, because it's not definitely anywhere, not until you measure it. This is one of the strangest aspects of quantum mechanics. Particles don't have definite properties until you measure them. Before measurement, they exist in a superposition of states, a quantum blur. And this applies to position. An electron doesn't have a definite position. It has a probability distribution. The wave function spreads out in space, and when two atoms get close, their wave functions overlap. The probability clouds intermingle, but even then, the electrons don't touch, because electrons are not little particles with definite positions. They're quantum objects, described by wave functions, and wave functions can overlap without the particles touching. It's probability overlapping with probability, not matter touching matter. Here's another thing, the Heisenberg uncertainty principle. This principle says that you can't know both the position and the momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you know the other. This is not a limitation of measurement. It's a fundamental feature of nature. Particles don't have definite positions and momenta simultaneously. They're inherently uncertain. And this uncertainty is built into the wave function. The wave function spreads out in space. It's not localized to a point. And that spreading means the particle is, in some sense, everywhere in the region where the wave function is non-zero. Not definitely in one place, but probabilistically distributed across space. So, when we say atoms don't touch, we're saying something even stranger than you might have thought. We're saying that the atoms don't even have definite boundaries. The electron cloud is not a sharp edge. It's a gradual fade out of probability. The probability of finding an electron decreases as you move away from the nucleus, but it never goes exactly to zero. In principle, there's a tiny, infinitesimally small probability that an electron could be found very far from its nucleus, across the room, across the galaxy. The probability is so small that it's effectively zero, but mathematically, it's not exactly zero. So atoms don't have hard edges. They're fuzzy. They're probability clouds with no sharp boundaries. And when two atoms interact, their fuzzy probability clouds overlap. The electromagnetic force between them depends on the overlap. The more overlap, the stronger the force. And the force can be attractive or repulsive, depending on the arrangement of electrons. But even with overlap, the electrons don't touch, because they don't have definite positions. They're spread out in space. Overlapping wave functions is not the same as particles touching. It's probability distributions interacting. And the result is a force, an electromagnetic force, mediated by the exchange of virtual photons. And this is where quantum field theory comes in. In quantum field theory, forces are mediated by particles. The electromagnetic force is mediated by photons. When two electrons repel each other, it's because they're exchanging virtual photons. These photons are not real photons. They're not photons you could detect. They're virtual. They exist for a very short time, just long enough to carry the force from one electron to the other, and then they disappear. This is allowed by the Heisenberg uncertainty principle. Energy can be borrowed from the vacuum for a very short time, and that borrowed energy can take the form of a virtual photon. The photon carries the electromagnetic force. It mediates the interaction. And the result is that the two electrons repel, but the electrons never touch. They exchange a virtual photon. The photon carries momentum and energy from one electron to the other, and the electrons move apart. This is the modern understanding of forces. Forces are not mysterious actions at a distance. They're mediated by particles, exchange particles. For electromagnetism, it's photons. For the strong nuclear force, it's gluons. For the weak nuclear force, it's W and Z bosons. And even gravity, we believe, is mediated by gravitons, though we haven't detected them yet. Every force is the result of particles being exchanged. And this is how the universe works at the fundamental level. Particles interact by exchanging other particles, and those exchanges create forces. But there's no contact, just exchanges, just interactions mediated by fields and particles. The universe is built on this principle, and it's a principle that Feynman helped develop. He was one of the creators of Quantum Electrodynamics, the theory that describes how electrons and photons interact. And his contribution was to show that you could calculate the probability of any interaction by considering all possible ways virtual photons could be exchanged. You draw diagrams, now called Feynman diagrams, that represent different ways the interaction could happen. And you sum over all the diagrams, you add up all the possibilities, and the result is a prediction for the probability of the interaction. And the predictions work. They match experiments to incredible precision. Feynman diagrams revolutionize physics. They gave physicists a tool for visualizing and calculating interactions. And they made it clear that forces are not mysterious. They're the result of particle exchanges. And those exchanges can be calculated, predicted, tested. This is the power of quantum field theory. It takes the abstract idea of forces and fields and makes it concrete. It gives you particles, virtual particles exchanging between real particles, creating forces, mediating interactions, and explaining why atoms don't touch. Because the interaction is mediated by photons, not by contact. So, here's the full picture. At the macroscopic level, you feel touch because electromagnetic forces push back when you press on something. At the atomic level, those forces come from the repulsion between electron clouds. At the quantum level, that repulsion is mediated by the exchange of virtual photons. Photons carrying electromagnetic force from one electron to another. And at every level, there's no contact. Just forces, just fields, just particles being exchanged. The universe is consistent. From the largest scales to the smallest, forces mediate interactions. Contact doesn't happen. And this is not speculation. This is tested. This is confirmed by countless experiments. From measuring the forces between atoms to detecting the particles that mediate forces. The theory works. The universe operates this way. And we know it because we've measured it. Feynman would emphasize that this is not just theoretical. You can test this. You can do experiments. You can measure the force between two plates of metal placed very close together in a vacuum. And you'll find that there's a force even though there's nothing between the plates. No air, no particles, just vacuum. And yet, there's a force. It's called the Casimir effect. And it comes from quantum fluctuations in the electromagnetic field. The vacuum is not empty. It's full of virtual particles popping in and out of existence. And those virtual particles create forces. Forces between objects that aren't even touching. This is measurable. This is real. And it's more evidence that forces are fundamental. Contact is not. Now, I want to circle back to the original question. Why does this matter? Why should you care? Because it changes your relationship with reality. When you understand that you've never touched anything, you start to see the world differently. You realize that your senses are giving you a simplified, interpreted version of reality. not the full picture. Your brain constructs a model of the world based on sensory input, and that model is useful. It helps you navigate. It helps you survive, but it's not the whole truth. The whole truth is stranger. The whole truth involves forces and fields and quantum mechanics. And understanding the whole truth gives you a deeper appreciation for how remarkable the universe is, how intricate, how elegant, how fundamentally different from what it appears to be. And there's something else. Understanding that touch is electromagnetic force helps you understand why the universe has the structure it does, why matter is stable, why atoms don't collapse, why you can build complex structures out of atoms and molecules. It's all because of the electromagnetic force. That force prevents atoms from collapsing in on themselves. It maintains the structure of matter. It allows chemistry to happen. It makes life possible. Without electromagnetic repulsion, atoms would collapse. Matter would not have structure. The universe would be very different, probably uninhabitable. So, the fact that you can't touch anything is not just a curiosity. It's a fundamental feature of the universe, a feature that makes complexity possible, that makes life possible, that makes you possible.